Hello friends, we are discussing the solution of radiative transfer equation. In the previous lecture, we discussed approximate methods. We discussed methods where we have approximated either the dimension of the problem, that is one dimensional problems, plane parallel slab or cylindrical geometry, or we approximated the properties of the medium as optically thin or optically thick. And we also discussed that these two type of approximations are little restrictive in the sense that in practical problems the solution or the domain of the problem is not one dimensional nor optically thick or thin. The third approximation that we are going to discuss in this lecture is based on the dependence of intensity on direction. So, the radiative transfer equation in a given direction, that means in a single direction, it is given by mu times di by d tau is equal to 1 minus omega I b minus I omega by 2 integration from minus 1 to 1 I times d mu. Of course, this is an integral differential equation and the problem is little difficult to solve analytically if we do not have some way to approximate the intensity function that appears in the integration. So, for one dimensional case it has been argued by Schuster and Schwarzschild, after which this method is based. The method is basically called two flux approximation or Schuster-Schwarzschild approximate methods. So, what this method basically assumes is that the intensity is isotropic, but the isotropic intensity may have different magnitudes in the upward direction and downward direction. So, how does an isotropic intensity looks like? As is represented by this image, at any point the intensity has same magnitude in entire 4 pi solid angle. If this is the case, this is called isotropic intensity. What Schuster-Schwarzschild assumed that although the intensity is isotropic, but it has different magnitudes in the upward and downward direction. So, the intensity will follow certain distribution in the upward direction with same intensity, and in the downward direction the intensity will be different, but it will be isotropic in all the downward directions. Okay. So, this distribution looks like this. We have different intensity in the upward direction and different intensity in the downward direction. Mathematically we can write this as intensity at any point in the medium bounded by two parallel plates, and in any direction mu is basically has two components, I minus and I plus. So, at any point in a given direction we have two components, I plus and I minus, and I plus and I minus may be different. I plus is the intensity going in the upward direction, I minus is the intensity going in the downward direction. So, for I minus, that is mu less than 0, and for I plus the value of mu is greater than 0, between 0 and 1, the intensity is different. So, when we do that, this integration that appears in the integral differential equation is simplified. So, substituting the expression of I in this equation, we get mu times di by d tau is equal to 1 minus omega I b minus I plus omega by 2 I minus plus I plus. So, we see that with this assumption or approximation on intensity, the integral differential equation has reduced to just differential equation, but this differential equation has to be solved on all the solid angles. This is in a given direction, this is in a given direction mu. So, we still have to integrate this equation over all the solid angles. So, we integrate over upper and lower hemisphere. When we do that, we basically get for this one, for I plus half di plus upon d tau is equal to 1 minus omega I b minus I plus omega by 2 I minus plus I plus. This is constant, so integration on this quantity does not affect. Similarly, on lower hemisphere we get minus 1 by 2 di minus upon d tau is equal to 1 minus omega I b minus I minus plus omega by 2 I minus plus I plus. Now, why this factor half is coming, I will just solve it for you. So, mu di by d tau we have to integrate over the upper hemisphere, that is 0 to 1 d mu. Now, on the upper hemisphere the intensity is constant as I plus. So, di plus we can take out, and in the integration we are just left with mu d mu and 0 to 1. So, this will be mu square by 2. So, di plus upon d tau mu square by 2 0 to 1, and this becomes half. So, this is why this half is coming, and in the negative direction minus is also coming because mu is less than 0. The boundary conditions again will be isotropic. On the upper plate we have diffuse and isotropic intensity given by radiosity J2 by pi, and similarly on the bottom plate the intensity is isotropic given by radiosity J1 and J2. So, I plus is J1 upon pi at tau is equal to 0, and I minus is J2 by pi at tau is equal to tau L. So, these are the boundary conditions. Now, we define incident radiation. So, incident radiation is integration of I over all the solid angles 2 pi minus 1 to 1 I times d mu, and this can be integrated by substituting the value of I from 0 to 1 and minus 1 to 0. So, this will be simply equal to 2 pi I plus I minus. Radiative heat flux similarly is defined as 2 pi integration over 1 minus 1 to 1 mu times I d mu, and this simplifies to pi times I plus minus I minus. Okay. So, this is the expression for radiative heat flux and radiative incident radiation. Now, we want to eliminate I plus and I minus because we do not know the these quantities. So, what we do is we add these two equations and subtract. So, let us call this equation 1 and let us call this equation 2. So, adding equation 1 and 2 will give us the value of radiative heat flux, and subtracting will give us the value of G. So, we get eliminate I plus and I minus. So, we get this expression for del dot q dq by d tau is equal to 1 minus omega 4 pi I b minus g, which is same expression which we have already discussed earlier. The relation between del dot q is related to incident radiation. We have already derived this result before. Okay. So, we get the same equation by adding by eliminating I plus and I minus. In together we get one more equation, that is dg by d tau is equal to minus 4 q. So, by adding the two equations and subtracting the two equations we get two equations, one is for del dot q and one is for dg by d tau. So, these two equations we have to solve. These are now ordinary differential equations which are very easy to solve. So, just by assuming the intensity to be isotropic we have eliminated the integration in the differential equation, and our equation has simplified to simple ordinary differential equations, two coupled ordinary differential equations. The boundary condition can similarly be found. So, our boundary conditions was I plus is equal to J1 upon pi and I minus is equal to J2 upon pi. So, eliminating I plus and I minus in terms of G and Q, we get G plus 2Q is equal to 4 times J1 and G minus 2Q is equal to 4 times J2. So, where we have added these two equations. So, G plus 2Q will give us I plus, which is basically the boundary condition at the bottom surface, and subtracting is giving us I minus, which is the boundary condition at the top surface. So, in terms of G and Q we have represented our equations and boundary conditions, and now these can be easily solved. Now let us see how this method can be applied to a simple problem where we have to find out heat flux within a non-scattering isothermal medium bounded by two isothermal black parallel plates at the same temperature Tw. So, plates are parallel and they are black. So, J1 is simply equal to sigma Tw power 4 and J2 is simply equal to sigma Tw power 4. They are black. So, the radiosity is simply equal to the emissive power of the black body. Okay. So, let us solve this equation. We write this equation first. So, we have the first equation is dq by d tau. So, let me just show you the equation. So, dq by d tau is equal to 1 minus omega 4 pi I b minus g, and omega is 0. So, this equation is basically simply equal to 4 pi I b minus g, 4 pi I b minus g, and the second equation is dg by d tau is equal to minus 4 q, dg by d tau is equal to minus 4 q. Okay. To solve this system of ordinary differential equation, we differentiate this equation with respect to tau. So, we get d square q by d tau square is equal to, now the IB is constant, this is isothermal medium. So, the first term derivative of first term will be 0 and this will be equal to minus dg by d tau, and this will be equal to simply 4 times q. Okay. So, our equation becomes d square q by d tau square is equal to 4 q. Let us call this equation 1. Now, this equation can be solved by complementary function method. So, we have this value of q using standard approach of solving ordinary differential equation, which we are familiar. So, q is equal to C1 e power 2 tau plus C2 e power minus 2 tau. This is the solution of radiative heat flux at any point in the medium. So, although the medium temperature is uniform, the heat flux is not, okay, it is varying at different locations. Now, let us simplify this expression further. So, boundary conditions we apply. So, boundary condition will be at tau is equal to 0. So, the first boundary condition was g plus 2q is equal to 4j1, g plus 2q is equal to 4 times j1, j1 is simply sigma t power 4. Okay. Now, we substitute for the expression for g. Okay. So, we substitute for the expression for g and we get 4 sigma t 4 minus dq by d tau is equal to plus 2q is equal to 4 sigma t w 4, where we have used the expression g is equal to 4 pi I b or 4 sigma t power 4 minus this is del dot q, this is a del dot q or dq by d tau. So, del dot q is 4 pi I b minus g. So, g is equal to dq by d tau 4 pi I b minus dq by d tau. So, that is what we have done. We have eliminated g in the expression by substituting for dq by d tau. Similarly, at tau is equal to tau L, the condition will be 4 sigma t power 4 minus dq by d tau minus 2q is equal to 4 sigma t w power 4. So, now this is the two boundary conditions we have. Okay. So, applying the boundary conditions. Okay. So, this was the solution. So, we apply the boundary condition here. Now, q is equal to C1 e power 2 tau plus C2 e power minus 2 tau, and dq by d tau is simply equal to C1 2 C1 e power 2 tau minus 2 C2 e power minus 2 tau, and we substitute the value of q and dq by d tau in these two boundary conditions. So, we get the expression for C1 and C2. So, this we get C2 is equal to minus C1 e power 2 tau L, okay, and this will be equal to sigma t w power 4 minus t power 4. So, this is the expression for the coefficient, unknown coefficient C1 and C2. So, C1 and C2 are related and the value of C2 is sigma T W4 minus T power 4. Now, the non-dimensional radiative flux psi is equal to Q by sigma T power 4 minus T W power 4. Okay. So, this value will be simply equal to e power minus 2 tau L minus tau and minus e power minus 2 tau. Okay. So, this is the expression for the radiative heat flux, and we can show the result in this chart. The result for the two flux approximation method is shown, and you can observe here. So, two flux approximation is basically the Schuster-Schwarzschild method, and we see that for optically thin case, that is tau L values very small, the method is exact. That means it always goes to correct optically thin limit, the values are correct for optically thin limit, and for optically thick cases we see that the method is relatively more accurate than the differential approximation method, which is the method we are going to discuss next, but still it gives good agreement for optically thick cases also. So, for this one dimensional problem between parallel plates, the two flux approximation method gives very good results for optically thin as well as for optically thick cases. The next method that we will discuss is the differential approximation or Milne-Eddington method. So, this method again is based on the approximation of intensity. As we discussed in the previous method, we approximated the intensity using isotropic with different upper and lower hemispherical intensity. This method is also based on the same concept where we are approximating the intensity. The mathematical procedure is little different than the previous method. So, what we do in this method is we take the starting point is the same integral differential equation for radiative transfer in a given direction mu, where mu varies from -1 to 1 or theta varies from minus pi to pi. We integrate over all directions, but before integration we multiply by mu power k. If so, we are multiplying by mu power k. Okay. If k is 0, it is called zeroth moment, and if k is equal to 1, we call it the first moment. In mathematics, this procedure of multiplying a quantity by certain quantity raised to power k and then integrating over all the values of that quantity is called moment. Okay. So, for example, I subscript k is basically known as kth moment of intensity, where the moment is defined as integration over all possible values of mu and multiplied by mu power k with intensity. Okay. So, this is the kth moment of the intensity. K is equal to 0 means 0th moment, and k is equal to 1 is known as the first moment. Okay. You must have heard this moment in moment of inertia, the first moment of area, second moment of area, and so on. Okay. So, this in mathematics this is called moment method. Okay. So, when we multiply by mu 0, that is 1, it is called 0th moment. So, we multiply first by 1 this equation, the radiative transfer equation, and integrate over all the solid angles. When we integrate over all the solid angles, the equation is basically transformed d I1 by d tau, where I1 is the first moment, and then the second right hand side simply becomes 1 minus omega 4 pi IB minus I0 plus omega I naught. So, again we see that we have got rid of the integral differential equation and we have simplified this equation in a simple ordinary differential equation. So, 1 minus omega 4 pi IB minus I naught is the first equation that we have obtained by taking 0th moment of this radiative transfer equation. Now, just to demonstrate you, let us take this quantity mu di by d tau. So, we have to integrate this quantity by multiplying by 1. So, we multiplied by 1 and then we have to integrate it with respect to mu, and the mu value varies from -1 to 1. Okay. Now, this quantity d by d tau we can take out. So, it becomes -1 to 1 mu I times mu d mu. Okay. So, this becomes the first moment. So, we just call it d I 1 d tau. Okay. And that is what basically we have got in this equation. Similarly, if we have just I and we want to integrate it with respect to mu, this becomes the 0th moment and we can write it simply I naught. Okay. So, we got this equation, let us call this equation 1. Now, what we do is we multiply by mu, that means we take the first moment and then integrate over all the solid angles. So, the first quantity becomes d I 2 by d tau and the right hand side becomes simply equal to minus I 1. Okay. So, this is the quantity that we have obtained. So, we have let us call this equation as 2. Okay. So, we have obtained 2 equations. Okay. Now, we have to define the boundary conditions and we have to do simplification, because in these 2 equations we have 3 unknowns I naught, I 1 and I 2, and we have 2 equations. So, we have to remove one variable here. So, what basically Milne Eddington did, they did the same thing what basically Schwarzschild did, assuming the intensity to be isotropic over both the hemisphere, that is the upper intensity is isotropic and the bottom intensity is also isotropic, although they may have similar or different magnitude. So, this approximation is basically the same, and we will see that it leads to similar equation that we developed for 2 flux method. So, we write the kth moment as integration over -1 to 0, where intensity is going to be minus I minus. So, 2 pi I minus -1 to 0 mu k d mu plus integration over 0 to 1 mu k d mu, and this quantity becomes 2 pi k plus 1 minus 1 power k I minus plus I plus. So, with value of k is equal to 2, this simply leads to I 2 is equal to 1 by 3 I naught, that is second moment of intensity is 1 by third of first moment of intensity, if we assume that the method the intensity is isotropic in such a way that upward intensity is I plus and the downward intensity is I minus. We should also observe that the first moment I 1 is basically I times mu d mu is basically nothing but heat flux, and we also observe that I naught, which is 0th moment, is nothing but the radiative intensity irradiation G. So, we replace I naught with G and Q with I 1, and what we get is this is the first equation that we had, dq by d tau is equal to 1 minus omega 4 pi I b minus G. So, this is same equation we had in the 2 flux method, and the second equation d I 2 by d tau is equal to minus I 1 is reduced to dg by d tau is equal to minus 3 q. Now, this is slightly different from the previous method of 2 flux where we had minus 4 q. So, the 2 flux method had minus 4 q and this differential approximation method has minus 3 q. Rest of the things are same, the boundary conditions are also same. Okay. So, for radiative equilibrium dq by d tau is equal to 0 and we get G is equal to 4 pi I b, and the heat flux equation reduces to minus 4 pi by 3 d I b by d tau. Okay. So, this thing we have already developed. So, the method, it turns out to be the mathematical procedure is entirely different. Here we have used the approach of moments, but because the intensity was approximated as isotropic, the governing equations are very similar. In fact, one equation is exactly the same as the 2 flux method. Okay, now, let us solve the problem and demonstrate how this method can be used to solve a practical problem. So, in this case we have again a non-scattering medium bounded by 2 plates, and the 2 plates are maintained at different temperature. Okay. So, let us say we have 2 plates. The bottom plate is at temperature T1, it is black, and the above plate is at temperature T2, okay, it is again black. So, we write down the equation dq by d tau is equal to, now omega is 0, it is not non-scattering medium. So, we get 4 sigma t power 4 minus g, and this is equal to 0. Why 0? Because radiative equilibrium. So, g is simply equal to 4 sigma t power 4. Okay. Now, the second equation dg by d tau is equal to minus 3 times q. Now, substituting for from this we get g is equal to minus 3 q tau plus some constant c, and this value is simply 4 sigma t power 4. Okay. So, we get g is equal q is equal to, basically we get c minus 4 sigma t power 4 upon tau. So, this is the expression for the radiative heat flux. Now, we apply the boundary condition. So, boundary condition are basically the same, g plus 2q is equal to 4 times j1, that is 4 sigma t1 power 4, and g minus 2q is equal to 4 times j2 is equal to 4 sigma t2 power 4. Now, the two plates are at different temperature. So, that is why j1 and j2 are not the same, but they are black. So, j1 is simply equal to sigma t1 power 4 and j2 is simply equal to 4 sigma t2 power 4. Okay. Now, we substitute the value of g in this case. So, we get this equation basically reduced to c plus 2q is equal to 4 sigma t1 power 4, because g is constant. So, c plus 2q is equal to 4 sigma t1 power 4, and this equation reduces to c minus 3 q tau L minus 2q is equal to 4 sigma t1 power 4. So, please note g is equal to, the expression for g is minus 3 q tau plus c, minus 3 q tau plus c. So, at tau is equal to 0, g is simply equal to c. So, this is at tau is equal to 0. So, we have substituted g is equal to c, and at tau is equal to tau L, g is equal to minus 3 q tau L plus c, and that is why we have this at tau is equal to tau L. Okay. So, we have written our boundary conditions in terms of q. Okay. Now, we will so we have the solution for q and we have to solve for this constant c. So, let us solve this. So, we get non-dimensional heat flux psi is equal to q by sigma T1 power 4 minus T2 power 4. Okay. So, from this equation we have to find out the expression for C using the boundary condition. We get this value as equal to 1 by 1 plus 3 by 4 tau L. Okay. Where now C has been found as equal to 4 sigma T14 minus 2q. The constant C from here 4 sigma T1 power 4 minus 2q is basically the value of the constant C. Okay. And the non-dimensional MSC power phi is equal to T1 power 4 minus T power 4 upon T1 power 4 minus T2 power 4, that is non-dimensional MSC power temperature power 4 is equal to 2 plus 3 tau 4 plus 3 tau L. Okay. So, this is the expression for non-dimensional MSC power, or basically a measure of temperature distribution between the two parallel plates. So, temperature or temperature power 4 or the MSC power varies with this expression, like as in this expression. So, we have basically calculated in this lecture the radiative heat flux and non-dimensional temperature distribution between two parallel plates using two different methods, the method of Schuster-Schwarzschild two flux approximation and the method of Milne-Eddington, the differential approximation, and the results that we have already shown before in an image show that the method of two flux is relatively more accurate for optically thick cases than this method of differential approximation. So, Schuster-Schwarzschild method gives better results than the Milne-Eddington method as far as the optically thick heat flux is concerned. So, thank you very much. In the next lecture we will discuss approximate methods, spherical harmonics and discrete ordinate method. These two methods that we are going to discuss in the next lecture are most widely used method for radiative heat transfer equation and are available in many commercial packages like ANSYS and STAR CCM. So, thank you for now.